All right, let's learn how to linearize data. So the first thing we have is this. We have a motorcycle drives down a test track. The following distance data was obtained. So at time 0 it went 0, and at time 8 it went 250. So number one, use the graph labeled non-linearized, and we're going to use it to plot the time versus distance data. So what we have is at time 0 the distance was 0, so I'll put a little dot here. And then at time 2, the distance was 17. So we are going to go over to time 2 and up to 17. Now notice, if this is 100 and this is 0, there's 5 of these, so we're counting by 20s. So I'm going to go over to 2 and up to right about here and put a dot. There we go. Close enough. All right. Now I'm going to go over to 4 and up to 62, it looks like. So I'm going over to 4 and I'm going to go 20, 40, 60. Again, it's hard to do it with this thing. Give me a break. Okay, now I'm going over to 6 and up to 146. So 6 and 1. Let's see. I think I'm right about there. And then I'm going over to 8 and I'm going up to 250. So there's 200, 250. All right, again, it's close enough. All right, so let's see, I've got that plotted on there. Just by looking at the graph, how can I tell that the motorcycle was accelerating? Well, here's how I'm going to tell. I'm going to look at it, and what I notice is I'm going to draw a best fit line, and the best fit line goes like this. See how it curves upwards? The fact that it curves upwards is what tells me. So, hang on a second. So the line is curved upwards, which indicates increasing velocity. Now let's try number 3. Calculate the time that's supposed to be squared. Sorry about that. The time squared values. So let's just do this. What I'm going to do is I'm going to say time is 0, and I'm going to square that and get 0. Now I go to time 2. The square of 2 is 4. So that's, the square of 4 is 16. The square of 6 is 36. And the square of 8 is 64. So what I do now is to linearize the data, what I did is I looked here and said that looks like an x squared function. So I took the x value and squared it. So instead of time, I have time squared. If I thought it was over x, I would have plotted 1 over x. If I thought it was the square root of x, I would have plotted the square root of x. But looking at this curve, I thought it was an x squared function, so I took the x variable and I squared it. That's how I got these values here. So now I'm going to plot the time squared versus distance to see what I get, and it should linearize if in fact it is a time squared function. Let's just see what I have here. Let me change the thickness of my pen a little bit here. Let's go back to this one here. Okay. Let's see. So 0 gives me 0. Then I'm going over to 4 and up to 17. So 4, I'm counting by 5s, so 4 and 17 is going to be right about there. And then I'm going over to 16 and up to 62. So let's see, I'm going over to 16, which is about here, and up to 62, which should be about there. 16 and 62 should be about there. And then I'm going to 36, and I'm going up to 146. So here is about where 36 is. 140, here's 100, 24, it'd be right about here. So let's put 1 right here. And then I go over to 64, and then, which is about, let's see, here, and I go up to 250, which is like, what about here? 64, 250, right about there. Hey, look, it lined up. So now I'm going to draw a best fit line here. So now here, it says draw a best fit line for linearized data. Notice, it did linearize. It was curved. Now it makes a straight line, which tells me it was a time squared function. And taking the slope of this line, I will be able to figure out the acceleration. But it's not as clear cut as you might think. There's a trick. So Draw a best fit line for linearized data. Let me make this a little bit thinner than I did last time. I didn't like how that worked last time. Let's do this one here. Alright, so let me try drawing a best fit line through the data. I'm going to think it's maybe like that. Good enough. Alright, so draw a best fit line. Calculate the slope. So remember, the slope is just the change in y over the change in x, so distance over time squared. So hey, look at here. Here's a nice data point. Look, 100 was right over 25. So I'm going to say the slope is 100 meters divided by 25 seconds. And that's going to equal, what's that equal? 4 meters per second squared, because I'm plotting squared seconds. Now remember, meter per second squared, that is an acceleration, but this is not the acceleration, and I'm going to explain why. Oops. So let's just move this up. Okay, so use the slope of the line to find the acceleration measure. And here's the important thing. Remember that the equation we're using is d equals 1/2 at squared. Here's d, here's t squared. The slope is 1/2 a. This is 1/2 a. How fast is my motorcycle accelerating? Well, if 4 is 1/2 of a must be 8 meters per second, or meters per second squared if you prefer. So the trick to this is, and the thing that kids are notorious for forgetting is, the slope of this line is not the acceleration. The slope of this line is 1/2 a in the equation d equals 1/2 a t squared. Since this is 1/2 a, you have to double this to get the acceleration. Let's try doing another one. Alright, let's see what we got here. Alright, complete the data table below using the graph on the left to find the distance values. Alright, I think I can do this. Let's see here. So if time is, I'm going to make this a little bit bigger. Let's see. Alright, here we go. Alright, so when time is 0, the distance was 0, and the time squared was 0. At 1, it looks like, let's see what we got here. If I go over to 1 and go over, I'm counting by 10, so I'm going to call that like maybe 3. I'm going to call that 3. And now, remember, this value here is time squared, not distance squared, but time squared. So what's the time squared value here? The time squared value here is going to be 1 squared, which is 1. You know what, let's just go ahead and do the time value so we don't screw up. So therefore, 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And 6 squared is 36. Now let's look at the graph to get our distance values at these different time values. So at time 2, it looks like it was about, I'm going to go with 12. And at time 3, I'm going to call that, what do you want to call it, 27? Let's go with 27. And at time 4, let's see, I'm going over to 4, I'm going to call that 48. 48. At time 5, I'm going to call it, let's see, if this is 50, this is 60, this is 70, I'm going to call it 75. And then at 6 seconds, I'm going to call it 110. Alright, let's see what we've got next. Well, sorry that this is on the back of it, so I can't show you the data on the front side, but let's just go ahead and do this now. So I am going to graph the linearized data from number 6. In other words, I'm graphing time squared, not time. So I'm going to look at the range of my time squared value, and I see that the largest time I have to get to is 36. So I'm going to have to arrange this axis so that 36 fits on it. And if I look, I think it won't work by 2s. 2, 4, 6, 8, 10. That's not going to work. I'm going to go by 5s. I could go by 4s, but I'm going to go by 5. So I'm going to say, all right, what we've got is, that's 5, 10, 15, 20, 30, and 40. That's how I'm going to do this. And now I'm going to plot my data. So when I had a time 0 value, I also had a distance value of 0. Then I'm going over to a time of 1 and a distance of 3, which is pretty much going to be right there anyway. Then I'm going to go to a time squared value of 4, and I'm going up to 12, which puts me right about there. And then I'm going over to a time squared value of 9, and I'm going up to 27, which puts me about here. And then I'm going over to a time squared value of 16, which is here, and I'm going up to 48, which is like here. So let's do that. So I'm going to 16, I'm going to here, and then that was a little high. And then I'm going over to a time squared value of 25, which is over here, and I'm going up to 75, which is going to be up here. Let's see, I think that's here. Again, a little bit too high. And I'm going over to 36, which is here, 35, 36, and I'm going up to 110, which is up here. So it looks like about there. And I didn't do a very great job here, but you did see it linearized. So question 8 says, what is the slope of the line? So I better draw a line here. Let me make my line a little bit thinner. Okay, that should work. I'm going to try to draw this. Okay, it's best to use a ruler. All right, I'm going to find the slope of this line. Here's how I'm going to do it. I'm just going to do this. Look right here. That's a nice data point there. I'm going to say that is, well, that's 95 and 30. So I'm going to say the slope is 95 meters divided by 30 seconds squared. Let's see what that is. Looks like it's about, it rounds to 3.2. So 3.2 meters per second squared, which is to say meters per second. But what is the acceleration? That is not the acceleration. Remember, d equals 1/2 a t squared. So therefore the acceleration is going to be double this. It's going to be 6.4 meters per second. How fast was the object going at the 6-second mark? Now remember, fast is velocity, and here's how I'd solve that. I'd say, well, at 6 seconds, I'm going to use this equation basically. I'm going to say acceleration equals the change in velocity over time. I'm looking for v, so what I need to do is I need to solve it for, I'm going to say acceleration is 6.4 equals change in velocity over 6 seconds. So 6.4 times 6 is going to be my answer. Let's see what that is. 6.4 times 6 equals, let's go with 38. It's about 38 meters per second. So let's continue on. Oh, I like this one. The image below shows oil drops left by cars that accelerated to the right. Okay. The car's engine left an oil drop every half second. That's important information. Not every second, but every half of a second. So I'm going to use the graph below to make a linearized plot of distance versus time squared. All right, whoops, let's see this here. So let's just collect some data here. So what we want to do is we're going to say distance, time squared. All right, so let's just start with times and times squared. So when the time was 0, the distance was, I'm going to start at time 0, and 0 squared is 0. And then I have, the next drop is at time 1/2. So that's 0.5. And 0.5 squared is 0.25. I can't believe I had to look on a calculator for that. 0.25. And then that's the 1 second mark. And 1 squared is 1. And then I have 1.5 seconds. And 1.5 squared is 2.25. And then I have the 2 second mark. So I have 2 seconds, and that's for Then I have 2.5 seconds, and that should be 12.5. I'm going to just do it anyway. 2.5 squared equals, whoops, pretend I didn't say that. It's 6.25. That is so embarrassing. How did that happen? 6.25. What was I thinking? Okay, and then I have 3, and then 3 squared is 9. That was so embarrassing. I can't believe I said that on tape. Okay, so I think we only went for 3 seconds. Let me double check. We went, that's 1 second, 2 seconds, 3 seconds, yes. Now let's get the distances that are associated with these. So at time 0, the distance was 0. At time 1/2, the distance was 0.5. At time 1, the distance was 2. At time 1.5, the distance was 4.5. At time 2, the distance was 8. At time 2.5, the distance was 12.5. That's a 5. And then at time 3, the distance was 18. I don't know about you, I cannot do this in my head, but that's what the graph is for. So this is just going to turn into magic. Really, all I want is how fast the car's accelerating, so I'm going to do what I've been doing on this whole thing. So, well, the first thing I'm going to do is figure out how to scale the axes, and I have to scale them not for time, but for time squared. So that means my time squared value, I have to get all the way out to 9. That shouldn't be too hard to do. Let's do it this way. Let's go like this. Let's call this, well, we'll go by ones. So we'll go 1, 2, 3, 4. We'll make that one. All right, 1, 2, 3, 4. What is that? 5, 6, 7, 8, 9. We'll make that one 10. Now let's label the y-axis. I'm sorry that this one had numbers already on it. I fixed that for most of your homework assignments, except for you, first period, apology. So we have to get, for the distance value, we have to get to 18. There's not 18 of these, so we're going to have to go by 2's, which means it's going to be 2, 4, 6, 8. Well, you know what? We can just call that one 10 instead of 1. We can call that one 20, and this one 30. Now let's plot the data on here. So let me get this to be a little bit fatter here. So you can go with that. Okay, what do we got now? All right, so we're going to go 0, 0. Then we're going to go to 0.5 and, I'm sorry, 0.25 and 0.5. Ooh. All right, this next one's going to be kind of hard. I've got to go to 0.25. You know what, let's just do this. Let's make sure we don't look at these. Whoops. Let's make sure we don't look at these. Okay, we're not doing t, we're doing t squared. Okay, so now we want to do 0.25 and 0.5. That's going to be hard to do. I'm going to try. I'm going to go to 0.25 and 0.5 is like there-ish. Okay, I could have done better. All right, now the next one is I'm going to a time squared value of 1, which is here, and I'm going to a distance value of 2. So that one I can do, no problem. It's right there. All right. Now I am going to go to 2.25 and up to 4.5. So 2.25 and up to 4.5 should be about right. Let's see, right about here. All right, and then we're going to go over to 4 and 8. Okay, we should be able to do that. 4 and 2, 4, 6, right there. I always seem to aim a little high here. I think this isn't calibrated right. And then we're going to go to 6.25, and we're going up to 12.5, which would be about here. And then I'm doing a terrible job aiming this thing. And then we're going to go to 9, and we're going up to 18. So here is, let's just see. So here is 9 and 18 should be like right here. Let's see if I can get that. Alright, now it seems like I always drift a little high. But anyway, let's just try drawing a best fit line. So to find acceleration, I have to have a best fit line. So let's try changing the thickness of this a little bit. Let's do this. Do it in blue. I'm going to draw best fit line. I'm going to find the slope of that line. I'm going to use this value right here. I'm going to call that 16 divided by 7, maybe? Does that sound right? Oh, you know what? Let's just use this. We'll use 8 divided by 4. Ha! Okay, so I do 8 divided by 4. 8 divided by 4. That gives me 2. But 2 is not the answer. That's half of the answer. So it's accelerating at 4 meters per second.